All right, lab four, magnetic braking with Faraday. Intro. In this experiment, I investigated the magnetic braking using Faraday's law of induction. The goal was to be able to observe how a falling magnet interacts with a conductive tube. The measure for the resulting motion and build a computational model that captures the same physics. The final objective is to compare the real experiment with the simulation and explain the underlying electromagnetic principles. Setup and procedure. I followed the Faraday's law actions and experiment instructions. Setup consisted of a very strong, yeah, I'm not even gonna try to pronounce that, magnet, a vertical aluminum tube, a ruler or tape measure, and a stopwatch. The magnet was dropped through the tube multiple times to measure the fall time. Control drop. A control drop was also performed to compare free fall motion with the magnet tube interaction. As expected, the magnet fell significantly slower inside the tube due to induced currents opposing its motion. Background physics. The slowing of the magnet is explained by Faraday's law and Lenz's law. As the magnet moves, the magnetic flux through each cross section of the tube changes. This changing flux induces circular currents, eddy currents, in the conductive tube. These currents create magnetic fields that oppose the magnet's motion. The result is a resistive force that reduces the magnet's acceleration. This is the essence of magnetic braking. And for the comparison, the magnet slowed dramatically inside the tube. The fall time is increased by a factor of 5 to 3, depending on the tube's thickness. The motion appears smooth with no oscillations. In the computational model, the velocity curve shows rapid acceleration at first, then flattening as braking increases. Terminal velocity is reached inside the tube, and the magnet speeds up again after exiting the tube. Comparison part 2. Agreement. The model data. The model captures the qualitative data. Oops. The qualitative behavior well. Reduced acceleration, terminal velocity, and re-acceleration after the exit. The differences are the real magnets have complex field distributions. Tubes conductivity and thickness vary, and the model uses simplified ring currents and uniform geometry. The what ifs. If resistivity were near zero, eddy currents would become extremely large, producing a very strong opposing magnetic field. The magnet will fall extremely slow, approaching a tiny terminal velocity. And how would the magnet's dynamics change? Acceleration inside the tube would drop to almost zero. The magnet will move downward at almost constant various small speed. What is part 2? If the holes or slots were cut into the tube, holes break the circular paths needed for eddy currents. Sorry about that. Weaker currents, weaker braking, and the magnet falls much faster. The effect on ring currents in the model, slots effectively increase resistance or remove conductive loops. Ring currents decrease, so the braking force in the simulation drops and terminal velocity increases. As for the conclusion, this experiment demonstrates how electromagnetic induction can produce resistive forces that dramatically alter motion. Both the physical experiment and the computational model shows that a falling magnet experiences strong braking inside a conductive tube due to eddy currents. The what if scenarios highlight how conductivity and geometry control the strength of the magnetic braking. This lab connects Faraday's law, Lenz's law, and real world applications such as magnetic braking systems, induction cooktops, and eddy current dampening.